Welcome to lecture series on digital electronics under EPG Pathshala. Today we are going to study one of the important topic in digital electronics, that is ALU. ALU stands for Arithmetic and Logical Unit. The computing power of any computer is decided by the processing ability of the ALU. ALU can be designed starting with simple logic gates, multiplexer and an adder block. Whenever we begin with designing ALU, we will be using a method called divide and conquer method. Here we will design arithmetic unit separately from logical unit. Once the functions of arithmetic and logical units are identified, the next thing is to prepare the function table. Once the function tables are prepared, we will independently implement arithmetic and logical units. These function tables can be then mapped such a way that arithmetic and logic unit could be integrated together. So, this is the principle that we are going to use for designing an ALU. We will start with simple 1-bit ALU design. The same principle can be extended to designing of 4-bit ALU. Once 4-bit ALU is designed, I am sure that the designer will get a confidence in implementing any n-bit ALU. So, in this method we will be learning about how ALU can be designed from 1-bit to n-bit, which is the most important part of every computer or electronic gadget. Learning objectives of this module are described first. In this module, the importance of ALU needs to be identified. Next objective is to design a simple arithmetic as well as logic unit. Further, different ALU design techniques will be explored. Finally, commercially available ALU IC will be studied. In the digital age, it is almost impossible to imagine that someone can live without computers. Computer is used in almost every aspect of everyday life. Computers mainly handles computations. The efficiency and the productivity of any computer are dependent on the type of CPU used in the computer. It is the brain of the computer. Arithmetic and logic unit is a digital circuit to perform arithmetic and logic operations. ALU is a fundamental building block of a central processing unit or a microprocessor of a computer. ALU can be implemented using simple logic circuits, which may include logic gates, adders, shifters, multiplexers, etc. The arithmetic and logic unit is designed to be the brain of the computer for performing arithmetic and logic functions. Basically, ALU handles the integer operations like addition and subtraction. In many cases, an ALU can handle either finite arithmetic or logical operations. Modern microprocessors, microcontrollers and embedded systems have very powerful and complex ALUs, floating point units, FPUs and graphical processing units, GPUs. Present superscalar processor have a separate floating point unit and integer ALU. The basic symbol of ALU is modified version of summation symbol. The CPU of the computer loads data from input registers to an ALU. The control unit of the processor tells ALU what operation to perform on that data. After the operation, control unit transfers the result of the ALU into output register. Operands A and B are the two inputs of an ALU. F is another type of input indicating the arithmetic or logic function to be performed on the operands. Y indicates the result of the operation and S indicates the status of the ALU result after the operation, like overflow, negative, carry output, etc. An ALU is the fundamental unit of any computing system. Understanding how an ALU is designed and how it works is essential to building any advanced logic circuit. Using this knowledge and expertise, we can move on designing more complex integrated circuits. The goal is to design n-bit ALU. Designing n-bit ALU is similar to the way we design n-bit adder. For an n-bit ALU, operands A and B are 8 bits each. Inputs at the selected lines decide the nature of arithmetic and logic operation. There are n bits plus 1 carry out at the output. The design begins with building a 1-bit ALU version. This 1-bit ALU can be built from logic gates, adder and multiplexer. Such 1-bit ALU can be combined together to get n-bit ALU. Let us first build the logic unit and then combine arithmetic block into it to make an ALU. Let us assume that the unit can handle two 1-bit inputs to produce a required output based on the function selector line. Let us prepare the logic diagram of a 1-bit logic unit. It operates on 1-bit operands. The simple logic unit contains 4 basic logic gates to provide 4 basic logic operations like NOT, that is complementation, AND, OR and XOR. To select one of 4 logic operations, a selector or a multiplexer is required. In this unit, a simple 4 to 1 multiplexer is preferred for designing of logic unit. To select one of 4 inputs, there are 2 select inputs S1 and S0. The function table assumes that both the data inputs A and B are present. The values of select lines decide the nature of operation to be performed on the operands. When the select lines are both 0 0, the logic unit complements the input present at input A. For S1 S0 is equal to 0 1, logical unit performs AND function. When S1 S0 is equal to 1 0, logical unit performs OR operation on the inputs. When both select lines are 1 1, the logical unit selects XOR operation. After designing the 1-bit logic unit, the next obvious step is to incorporate an adder block to the logic unit. A full adder allows the unit to perform addition as well as subtraction. Inclusion of full adder implements simple 1-bit ALU. This 1-bit ALU performs 4 logic operations and 1 arithmetic operation. So, for example, addition. To select one of 4 logic operations and addition, multiplexer with 5 inputs is required. In this unit, a simple 8 to 1 multiplexer is preferred for designing of logic unit with adder. To select one of 5 inputs, there are 3 select lines S2, S1 and S0. 3-bit binary input combinations are required to select inputs to obtain 1 arithmetic and 4 logic operations as shown in the function table. The function table assumes that both the data inputs A and B are present. The full adders have 3 data inputs A, B and Ci with sum and carry as outputs. The values of select lines decide the nature of operation to be performed on the operands. A careful observation of select input S2 indicates an interesting thing. When S2 is equal to 0, the ALU performs logic operation, and when S2 is equal to 1, then it provides arithmetic operation irrespective of the values of S1 and S0. After addition of operands, sum as well as carry outputs are generated. For implementing subtraction, it is necessary to upgrade ALU. The subtraction can also be represented as an addition of A with B's complement. By adding 1 through the carry input, it is possible to implement 2's complement addition. In this diagram, addition of 1 2 to 1 multiplexer at the input allows us to select either B input without or with complement. The adder with multiplexer can help us combine adder and subtractor circuit together in a single unit. B invert input value decides whether to perform addition or subtraction. It should be noted that the value of B invert should be 0 to perform logical operation. The function table for 1-bit ALU has 3 select inputs, B invert and C in, and Y is the output. When S2 is equal to 0, ALU performs logical operations, whereas S2 is equal to 1 results in arithmetic operations. The value of carry input for arithmetic operation generates addition with or without carry. When B invert is equal to 0, multiplexer will send B directly to the multiplexer, which enables the addition. If B invert is equal to 1, then inverted input will be taken and transferred to the adder, which performs subtraction. Carry in with B invert input generates numbers for 1's complement and 2's complement form to carry out subtraction. From the design of 1-bit ALU and function table, it is clear that it is possible to perform addition as well as subtraction through an ALU. Let us consider the design of n-bit ALU. It is possible to cascade 1-bit ALU to construct n-bit ALU. With this concept, it is possible to extend the concept to 4-bit, 8-bit, 16-bit or 32-bit ALU. Operands A and B are connected bitwise to individual 1-bit ALUs. Such design is also referred to as bit slice ALU design. In cascading, the input carry is applied to the first 1-bit ALU and the final carry is obtained from the last 1-bit ALU. Select lines and B input lines along with invert lines are connected in parallel to all 1-bit ALUs. Select lines can decide on the nature of operation like arithmetic or logic operation. The binary values given to the select lines along with B invert and carry in decides the final function output as n-bit arithmetic or logic output. The function table for n-bit ALU can also be prepared on the similar lines of 1-bit ALU. The ALU design process begins with the specifications of ALU. Step 1, identify arithmetic and logical functions needs to be implemented. Second, start with the word problem or description of the function table. Third, use divide and conquer approach, that is, design arithmetic and logic unit separately. Step 4, for arithmetic unit, map the function table to the adder and build the input logic. Step 5, for logic input, use basic logic gates and multiplexer for implementation. And last step, integrate arithmetic and logic unit. Let us now consider a 4-bit ALU design. The first step in designing the ALU is to identify the arithmetic and logic function specifications. Now consider a function table for 4-bit ALU with a list of different arithmetic and logic functions separately. There are 8 arithmetic functions like transfer data, increment, add, add with carry, 1's complement and 2's complement subtraction and decrement. In addition, there are 4 logic functions AND, OR, XOR and NOT are to be implemented. From the set of functions, it is clear that there are 3 select inputs, namely S2, S1 and S0 required for arithmetic functions and 2 select inputs S2 and S1 for logic functions. Next step is to use divide and conquer approach, that is, design arithmetic and logic units separately. Let us design arithmetic unit first. Arithmetic unit can be implemented using 4-bit adder with A and B as operands and sum and carry as output. In the next step, for arithmetic unit, map the function table to the adder and build the input logic. The 4-bit adder receives external inputs xi and yi. Xi's are connected directly, whereas yi's are connected via input logic circuit to have correct mapping of function table. As a next step, build the input logic required for the B input of the adder. Let us now find out required adder inputs from the function table. At this moment, let us consider the adder inputs, and the input should be such that it should provide 8 desired arithmetic operations. Careful observation of the function table indicates that for all external inputs, operand x is connected to a input of adder. The nature of arithmetic function decides B input and carry Ci input condition. For example, data transfer operation requires B and Ci inputs as zeros, whereas increment operation B input is 0 and Ci input is 1 to get the desired effect. Similarly, condition can be obtained for addition and addition with carry and so on. For decrement operation, it is directly the subtraction which must be implemented, hence B input contains all 1's. In short, what is required to compute input B is given in the arithmetic unit to input y, and the functional select code can provide the necessary output. The logic unit supports different logic functions on 2 multi-input xi and yi, producing the output gi. The logic function table indicates that there are 4 possible functions AND, OR, XOR and NOT selected by the logic select lines. Functional select code decides the nature of operation to be performed in logic unit. This table can be implemented using multiplexers and few basic gates. It should be noted that for n-bit logic unit, we need a 4-to-1 multiplexer. Last step is to integrate the function table of both arithmetic unit and logic unit. The combined function table of both arithmetic and logic function units together is shown here. Let us incorporate the select line S3, which is equal to 0 for all arithmetic functions and logic functions when S3 is equal to 1. There are already 3 variables in the arithmetic function table. Here S2, S1 and S0 selects the desired function. The complete ALU diagram integrates both AU and LU. Arithmetic unit performs the arithmetic functions and logical unit performs the desired logic functions on 4-bit xi and yi decided by the select lines. Select line S3 provides input to connect the select input of chord 2 to 1 multiplexer, which is either selecting AU or LU. For 4-bit operands, 4 2 to 1 multiplexers are used. Arithmetic unit can also generate a carry output. Arithmetic and logic unit is very popular device which is capable of performing different arithmetic and logical functions. Basically, ALU is the main part of central processing unit of any computer. Let us study commercially available TTL IC, that is IC 74181. It is one of the popular and most widely used ALU. The logic symbol of IC 74181 is shown here. IC 74181 is basically a 4-bit ALU which can perform all the possible 16 operations on 2 operands and variety of arithmetic operations. Let us now talk about certain features of IC 74181. Features of IC 74181. There are 3 important features. First, it can perform arithmetic modes, like it can provide you certain functions like addition, subtraction, shift operands, a 1-bit position, magnitude comparison and 12 other arithmetic operations. Whereas under logical function modes, there are XOR, AND, OR, XOR, NAND, comparator and 10 other logical operations. And third, it also provides full look ahead logic for high speed operations on a longer word. The IC 74181 is an arithmetic logic unit, that is ALU. This ALU is capable of performing 16 binary arithmetic operations on 2 4-bit words. These operations are selected by 4 function select lines S3, S2, S1 and S0, and includes addition, subtraction, decrement, increment and state transfer. The arithmetic and logic functions can be selected by selecting the mode M. If M is equal to 1, then logic operations on the operands are performed. Similarly, when M is equal to 0, ALU performs the arithmetic operations. The operations on active low operands and active high operands can also be included. In addition, there are 2 additional lines, carry in and carry out, which are provided for cascading and generate n numbers of ALU. The device also provides internal carry look ahead and provides either ripple carry between the devices, which is represented as Cn plus 4 output. For carry look ahead between multiple ALUs, using single carry propagate P and carry generate outputs are normally used. Let us now summarize the things that we have studied in this module and consider some of the take home points. Initially, we have studied what the ALU is. ALU is basically arithmetic and logical unit, which is the heart of every CPU. Central processing unit or a microprocessor is used in almost all computers, communication gadgets or control units. The processing ability of every unit is decided by the capability or the computing power of the ALU. When we talk about the computing ability of the ALU, it basically tells us something about how many arithmetic and logical operations could be performed. Now, to describe this, we need to understand the method of designing the ALU, and that is what we have studied in this module. In this module, we have started with designing simple 1-bit ALU. While designing 1-bit ALU, even we have simplified how to design arithmetic unit separately from logical unit. Now, to implement logic unit first, we have identified 4 basic functions AND, OR, NOT and XOR, and these basic logic gates are connected through the multiplexer, simple 4 to 1 multiplexer, to get the desired operation. The function select lines can allow the designer to select one out 4 operations, whereas in case of arithmetic unit, we need to talk about how many arithmetic operations are to be implemented. And we have started with simple arithmetic addition, like simple 1-bit addition can be extended to 4-bit and n-bit operations. This addition operation can be extended further such a way that we can even perform the subtraction using adder. We know that addition with 1's complement number or 2's complement number can give us really the subtraction. So, logical unit along with a adder and one multiplexer can give us basically some kind of arithmetic and logical unit design. So, this is about 1-bit adder that we have seen. The concept of 1-bit adder is repeated 4 times, that means the same unit is repeated 4 times, and cascading along with the carry input can allow you to design 4-bit ALU. This 4-bit ALU will have once again similar features of arithmetic and logical functions. The same concept could be extended further to n-bit ALU. Now, while designing the n-bit ALU, we have studied a simple 6-step procedure, and that procedure is clearly defined. In addition to that, we have studied commercially available IC, TTL IC specifically 74181, which basically performs 16 arithmetic operations and similar 16 logical operations. The inputs could be inverted or uncomplemented inputs, and the outputs what we get could be selected by the select lines. So, just to sum up, we have started with the simple 1-bit design and we ended with simple standard ALU IC. Thank you.